In this video, we're going to talk about esters, and we're going to go through some exam style questions where we have to split up those esters and look at other aspects of ester questions. We think in this video, you should make sure that you stop the video, do the question, and then look at the explanation. So don't make this passive. Use the video to answer those questions before the explanations. So let's get on with it. So we have an exam style question here where we have an extra amine group. And this is this amine group right here. And we're going to do acid hydrolysis. So we're going to hydrolyze this with acid. The first step we have to do is look at where the esters are. So if we're looking at the esters, that's where we're going to get our hydrolysis. So our ester, first one, is going to go here. There's the first bond we're going to break. We then track along and look for the next ester. The next ester is here. So we are going to then break that bond. So we've broken both of the bonds, which means we're going to have three products. One product up here, another in the middle, and then another one down there. They deliberately put the amine in for two reasons. One, because they want you to think that that might break. It won't. Leave it the way it is. The other bit we'll explain in a second. So three different products. So we'll do three arrows. So there you go. And the last one over here. So we are going to start with the first one. So all we do is redraw it out, as we've done in previous videos, just like it is. So I'm going to redraw that one out. Okay, and then that's got the O. All I've done is redraw that. Then I'm going to go to this arrow here. We're going to go for the middle one, starting at this carbon right here. So there you go. There's my double bond O, which then goes down and then goes up and down. You see I've done this like that, and then I'm going to put it down. Okay, so I've done this section right here. Then it goes across to the NH. Okay, and it will go to, let's put the H like that on that one. So we've done this NH, and then it goes, and you've got this bit here. Okay, and then we stop. So that's our middle section. You see we've drawn our middle section. We then go to our final section, which is starting from up here. So we start from our oxygen. Okay, then it goes down, then up. Then goes down. I'll go to our carboxylic acid. Okay, so we have done just literally broken up the esters. That's all we've done and created three different products. Now, from that point, we then start adding the waters back in. So the waters back in, so that, as we've done in previous ones, where there is an ester bond, the ester bond was between these different parts here, we'll add the H and we'll add the OH. So we've added water and we've added the H that side and the OH that side. Then we do the same thing here. And we'll have our OH that side and our H that side. So we put the water back in where the ester bonds were. So at the moment, this would get you 3 marks. One there, one there, one there. But it wouldn't get you that 4th mark. So I'm going to need to take you back to this. So this says acid hydrolysis. So we're hydrolyzing this with acid. So we now need to look along the molecule and say which part of the molecule will react with an acid. That won't react with an acid, okay, especially not a weak acid, but you've got the carboxylic acid here, carboxylic acid, they won't react. Then you've got the OH again here, you've got the carboxylic, they won't react. But the important thing you've got to look at is this part right here. Okay, so on there, which I have not shown, is a lone pair of electrons. Now if that has a lone pair of electrons, you can actually react with an acid. So that means it can act as a base. Now the simplest way of looking at this sometimes is if we have something like NH3. So if we have NH3 and we add it to H+, we end up getting NH4+. And the important thing here is that the charges each side balance, so the plus, and you can see this H is donated. This is a dative covalent bond because the lone pair of electrons has been accepted by the H+. That essentially means there are too few electrons, too few electrons, because remember the H doesn't have any electrons at all. So you're few of one electron, which means you get a positive charge. And the interesting thing is when this happens in other areas as well, so for example, water can act in exactly the same way. Okay, and that can make H3O+. And there's a little tip when it comes to doing this is, if you see that, that there's an extra bond to nitrogen or oxygen, it will become plus. And you can see that generally. And so generally that works. Okay, so if you look at this point, we can then say, right, okay, there's a lone pair of electrons right there. If there's a lone pair of electrons right there, this H from the acid hydrolysis, so remember, we're doing acid hydrolysis. Okay, acid means this is done H plus / H2O. So we've added our H2O, and now we're going to add our H plus. Okay, so our H plus is going to react with the base. So there's your H, and that means there's two H's on that, which means there's too many bonds to the N, which means it ends up having a positive charge. You can shorten this if you want, just to NH2 with a plus on it. But that is your extra mark. So if we're going along here, we're going to get a mark for this, we're going to get a mark for this whole thing here, mark for here, and then potentially getting a mark for the fact that we know that amine reacts with our hydrogen. And remember, you can shorten that down to just NH2 plus if you'd like. And that's how you do acid hydrolysis of a really complex molecule using H plus / H2O, adding the water first, and then after you've added the water, seeing whether the acid reacts with anything. And if there's an amine, it's going to react with the amine and protonate it, because the amine is a base and donates a pair of electrons. We're now going to go and do a question using structural formula. And I want you to know, if you're going to do structural formula, you can also write out your answers in different formulas, unless the question stipulates. So if you're not 100% confident with the formula you've got, you can use displayed or you can use skeletal as well, unless it stipulates the type of formula you must produce. So let's look at the question. There is an equation for the hydrolysis of the ester to be produced, and it gives it to you in this formula here. Because what we're going to do is explain and convert that formula to kind of go through how you do that, and also go through the reaction with sodium hydroxide. So let's put this over to the side. And so there's our formula, and here's our sodium hydroxide. So if I start writing this out, and we have our CH3, C, and then that's COO, and then CH2, CH3. So there's our formula, as over there, and we're adding to it sodium hydroxide. Now, the important thing is that it's aqueous sodium hydroxide, so we'll put NaOH aqueous. But the important thing to remember, this is really, really important to remember, okay, that this is essentially sodium hydroxide and water. Okay, so as we've done in all the previous questions, we have got to look at it as sodium hydroxide and water. Now, just for those of you who are not sure about this formula, let's go, it goes from left to right. So if we draw it out in a slightly different way, okay, and this is our CH3 that we've got here. And then we'll go to the carbon, so we're just working our way along. Okay, so there's a carbon there. Go to the next carbon, which is our COO, which is a COO group like this. And then it goes to our CH2, CH3. So that's that drawn out in a slightly different way, which is, I think, quite helpful in terms of understanding this formula. Now, we do, like we've done every single other one, we break the ester bond, and then we break the ester bond, and we then redo. So if that's the case, my CH3 comes back up again, and then C, and then O, O, and I've broken that bond, so I'm going to leave it like that, because that is this section that I've drawn here. So that's the section I've drawn there. I'm going to draw the other section. That's my other section, and again, this is that section here. So I have got my two sections. Now I'm going to think of my sodium hydroxide and my water. So my sodium hydroxide and my water, first thing I'm going to do is add my water in. So remember, as we've done in all the other ones, it's there and then we go here. We've turned it into a carboxylic acid and an alcohol. Then remember, we are using sodium hydroxide, so therefore the hydroxide will react with the acid and remove this H. Okay, so that H will be gone. Okay, so that's totally gone. And then we can put our Na in its place. And there you go. And there you have your two products. Now just to show you what that looks like in terms of a bit like the formula there, that means that is going to be your CH, your C, CH3, okay, and then that is that. And then that is that. And then obviously you just have your alcohol. So this is your sodium salt that you produce as a result. And remember, you have to include the sodium because it says sodium hydroxide there. If it was OH minus, you would not have to include the sodium. It would just be a negative charge. Okay, and this is your full formula, which is basically going from this ester plus the sodium hydroxide going to your salt, okay, going to your alcohol. And that is how you do hydrolysis of an ester using structural formula instead of skeletal. We're now going to go on to do a couple of MCQ questions which are common in exams on these esters. We have an ester right here. We want to know what reagents you could use to prepare that ester. So methanoic acid and propan-1-ol, methanoyl chloride and propan-2-ol, methanoic anhydride and 2-methyl propan-2-ol, and 2-methyl propanoic acid and methanol. I just want to talk about the question a little bit first. So you notice that there's a comparison here, and often in the MCQ questions they will have a few answers that are really, really similar, so you have to weigh them out, but they'll always have one that's obviously completely different. So you can see here at the bottom, 2-methyl propanoic acid is completely different to the meth, and the meth. So it's more likely that that is not the right answer to make this ester. And at the same time, that means if I look over and I look at this propan-1-ol, propan-2-ol, 2-methyl propan-2-ol, you can see that there's a really distinct difference between there. So you can try and look at the question for the differences first and see the similarities, for example, the meth, but then look, there are differences on the other side. So why don't I look at, for example, my first port of call might be the fact that I look at the alcohols first and see whether they fit. So let's do that. Let's put this over to the side and let's do that. So first of all, we need to look at the ester itself. So I've highlighted it up there, but if we draw it to make it a little bit more clear, there's our ester group, and we're going to do our alcohol group now with these three CH3s. Okay, and then our H coming off there. We then look at it and go, right, okay, it's got to come from an alcohol, for example, and a carboxylic acid to start off with, and we break that ester bond. Now, if that is the case, we can now draw the alcohol and, for example, the carboxylic acid that it comes from. So let's draw the alcohol first because we think the alcohol is the difference because we've looked at the question. And we can see that this alcohol is okay, and there's my alcohol, and this is just that group that is there, and that's it. We then go for this side, as we've done in other questions, and we draw that out. Again, we've just split this bond. And then we know that when you do hydrolysis to create the products, again, you add water. So we're just going to add water to it. Okay, and we'll put that water back in. So there's our water that is placed back in. So let's look at this first of all. Let's look at the alcohol and say, what kind of alcohol is this that I've made it from? Because it has to be an alcohol that you react it with to make an ester. This can be slightly different. The acid can be slightly different. You can make them from acyl chlorides, which is in B. You can make them from acid anhydrides. So let's look at this alcohol first. If you look at this alcohol and I draw it in skeletal formula, okay, I think it's a bit easier in skeletal formula. There's 3 carbons in a chain there. So there's my 3 carbons in a chain. There's a methyl coming off position number 2. So if this is 1, 2, and 3. Okay, position number 2, there's a methyl coming off. In position number 2, there's also an OH coming off. So we have our compound. A bit easier to name now because I can then say this is 1, 2, and 3. So this is 2-methyl. There's a methyl coming off the bottom there. Propan, because there's a chain of 3. 2-ol. So 2-methyl propan 2-ol. So I'm going to come across here. I'm going to look for 2-methyl propan 2-ol. Well, that's in C. That's a completely different alcohol. That's a completely different alcohol. That's a completely different alcohol. So basically what we're saying here is my right answer has got to be C. Okay, so C definitely going to be our right answer. But let's go through it in total just to make sure you can see why it is C. So first of all, methanoic acid, methanol chloride, methanoic anhydride. We can see that this carboxylic acid has 1 carbon in it, 1 carbon. So therefore it could have been A, B or C. Now you can make esters by adding an acyl chloride. So we could turn this into an acyl chloride. So let's turn it into an acyl chloride. If you add an acyl chloride to that alcohol, you would make the same ester. Okay, and if you do the anhydride I'm going to put down here. So the anhydride is going to be, there's your anhydride section. And it's methanoic anhydride, so 1 carbon on each side. So basically, if I took the acid, or I took the acyl chloride, or I took the acid anhydride and added it to that alcohol, I would still make this ester. They would all make this ester, but C has the right alcohol. So therefore, methanoic anhydride plus 2-methyl propan 2-ol is the right answer for this question. We're now going to move on to our last question, which is about whether a compound can be hydrolyzed or not. They can often give you a set of reactions and just ask you to say which one is the type of reaction they state. And in this one, it's hydrolysis. So think to yourself, what is hydrolysis? Well, that is adding H2O predominantly, and can also be nucleophilic substitution in AS where you add sodium hydroxide to haloalkanes. But predominantly, it's adding H2O. So we've got our options. Our options are a carboxylic acid, then we're going to go to a acyl chloride, then to an amide, and then to an ester. And think to yourself, which one of those can you add water to, or OH- to, and it will react. So let's move this over the other side. Let's remind ourselves of those hydrolysis reactions so we can answer the question. So acyl chloride to carboxylic acid. That is H2O. You just add H2O, so it's definitely a hydrolysis reaction. We then go esters to carboxylic acids and alcohols. You can do that through H plus slash H2O or through OH minus H2O. And that is definitely hydrolysis because we have this water again. Then we have amides to carboxylic acid and amines. Same reaction really as esters. And you can use H plus H2O, OH minus H2O. Again, hydrolysis because of that water. And then we have the weird one, which is nucleophilic substitution of haloalkanes. And that's with OH minus or sodium hydroxide. Now, if that is the case, should be looking across here and say, right, okay, which one do I think cannot be hydrolyzed? Well, I've got an acyl chloride here, so this B is an acyl chloride. So therefore, that'll be our first one. So that's done. That's definitely hydrolysis. Then we go to C, which is an amide. Well, an amide is here, and that is hydrolysis. And then we go to the bottom one, which is an ester, which is up here. So that is hydrolysis. I skipped the top one because of what it was. This is a carboxylic acid. You cannot see a carboxylic acid in this list, and therefore A cannot be hydrolyzed. And because it can't be hydrolyzed, the answer to this question is A. And it's really useful to be able to do these questions and know the reactions that come under a certain title, for example, nucleophilic substitution, electrophilic addition, electrophilic substitution, such and so forth, and hydrolysis and oxidation, and also reduction. So practice makes perfect with this. Attempt as many questions as possible on this type of thing.